Welcome to Calculus 1, Lesson 1A, Introduction. Once upon a time, there was a guy named Isaac Newton, and he invented calculus. But there's also a guy named Carl Friedrich Leibniz, who also thinks he invented calculus. At any rate, calculus is what we're going to start learning today. We're going to start with, what even is calculus? Calculus is math that explains velocities, accelerations, tangent lines, slopes, areas, volumes, arc lengths, centroids, curvatures, lots of things that come up in applications of science and otherwise. It allows a lot of different fields to model real life behavior in ways that you couldn't do otherwise. What's the difference between calculus and pre-calc or algebra? Well, calculus is very dynamic. Things move around and change in calculus, whereas pre-calc, everything is static. It's staying still, and you're trying to see what is the nature of this thing while it's staying still. So let me build math from the ground up to calculus. We've got this thing called arithmetic. This is something that you learned in elementary school or started in elementary school. And basically, arithmetic is doing stuff with numbers. Adding, subtracting, multiplying, excusing your dear Aunt Sally, stuff like that. From there, we've got algebra. Now, we're going to have numbers that are in some way arbitrary or unknown. So algebra is doing stuff with variables and functions. And then, building on that, you've got pre-calc, which I would say is learning more advanced stuff about specific kinds of functions. Trig, logs, exponentials, more detail than you'll ever need about polynomials. Now that you know how functions work, we can go on to calc, where we can talk about how things change. And that's where we're headed. Let me adjust my camera a little bit here. Here's some examples. Let's say we have an object traveling with a constant velocity. I don't have a ball on my desk, for shame. But if you picture, a ball rolling along a frictionless surface, that would be, theoretically traveling at a constant velocity. We can do that with algebra. We can analyze that with algebra. We can say, how fast is the ball going and where will it be after 10 seconds? But the minute you add some kind of acceleration or deceleration to that, and that includes turning a corner or going down a hill or having friction, now we need calculus and beyond in order to really look at that. Another thing we talk about a lot in calculus is this idea of steepness. Now, when you have a linear function, we look at steepness by talking about slope. But what about if something is curved? The way I draw this, let me tighten that up a little bit, actually. got some kind of curve like this, in some way, the curve is steeper here than it is here. Right? Which part would you rather climb? Okay, and we talk about this with something called a derivative. Then there's how tight a curve is. Picture you're in your car and you turn a corner. If you're going faster, then you feel that lateral g-force more, pushing you towards the side of the car. And the tighter that turn, the more you feel it. So we've got, this looks like it could be part of a circle. How tight is that curve versus how tight is the curve that makes up that small circle or this bigger circle? But tightness of a curve can change throughout a shape. This is tighter in here than it is out here. You need calculus to talk about all those things. Calculus also wants to talk about area. Now, you've probably done some areas before. I've got a rectangle, triangle, circle, ellipse. These things don't need calculus. But what if I wanted to draw a sine curve and take the area underneath it? That is something you need calculus for. Trying to get the camera just right. That's good. And now let me focus button. There, that's pretty good. We can also talk about volume. We know that the volume of a cube-like thing, a rectangular prism, that's not legible, length times width times height. And we know that the volume of a sphere is 4/3 pi r cubed. And with the skills that we have right now, if I gave you the dimensions of such a prism or such a sphere, I think you'd be able to calculate the volumes of those things. But why? Where do those formulas come from? Why do they work the way they do? Calculus is needed to answer those questions. Specifically in Calc 3, you talk about three-dimensional objects. Here's another cool thing that calculus can do. If you've got some curve, this is some function, some f of x, and you take that and rotate it around the x-axis. So what I'm talking about is it can jump off of the page and rotate like this. And as it rotates, it like leaves behind a trail of its volume. So where this area has traveled, it's filling in, right? So you end up with a shape like this. What is that? That is a flower pot. See, there's a flower, and then it's got little petals. See, so calculus can tell us things like the volume of a flower pot or the surface area of it, right? Like how much clay does it take to make this thing, or how much water can fit in this thing. So what this means is all you need to know is you need to find a function that closely follows the side of that flower pot and then picture rotating it. And then calculus can answer those questions for you. Okay, so now how exactly are we going to bridge the gap between where we're at with our pre-calc knowledge and where we want to go with our calculus knowledge? Well, here we are over here with our pre-calc, and we want to get over here to our calc, and there is something we need to do to build a bridge and get across. So here's my bridge. I'll even give it like a little railing. There we go. That looks pretty safe. This bridge is called limits. So Unit 1 of this course is going to be all about limits, what they are, what they mean, and how to do things with them. Okay? From there, we're going to talk about things like tangent lines. So what is a tangent line? Tangent line means I might be interested in a line that is just touching this curve at that point. Okay, a tangent line is a line that lies very, very flat against a curve. Okay, well, with the knowledge that you have right now, you wouldn't be able to find that, but some basic pre-calc and algebra techniques can let us talk about secant lines. So if I zoom this picture out, it will look like this. Here's the tangent line that we want. And then there's the secant line that we can get to come pretty close. And we construct that to hopefully make it come quite parallel. And then we use a limit to bring this line closer to that one so we can find exactly what we're looking for, right? So if we want to find the slope of this pink line, we talk about the slope of this blue line, the secant line here. You might have heard that called average rate of change in a pre-calc or algebra class before. Now let's talk about how that slope of a secant line is calculated a little bit. So we're eventually going to be interested in picking some x value, c, and then finding the slope of the tangent line on a curve where the x value is that c, right? So the coordinates of this point, let me make that pink. The coordinates of that point are c, comma, f of c. All right, so to make a secant line, I'm going to take c and I'm going to add just a little bit more. So I'm going to call this other x value c plus delta x. Okay, now the triangle is a Greek letter, delta. It means change. So we're doing our same x value that we're interested in, the c, plus some little change in x. All right. And then if I evaluate that function at c plus delta x, I get this point here. Now what's the y value of that? All I know is it's f of that c plus delta x. The secant line that I'm interested in now is this one. So coordinates c plus delta x, comma, f of c plus delta x. Okay, well, now we have two lines, or 2 points, and we want to find what would be the slope of a line that passes through both of them. This is an algebra question. We know that slope is rise over run, or change in y over change in x, right? So what's the change in y? It started at f of c, and it finished at f of c plus delta x. And then what's the change in x? It started at c, and it finished at c plus delta x. All right, well, look what happened here on the bottom. I've got a c and a minus c. Those are going to cancel out. And I end up with f of c plus delta x minus f of c. So your change in y over the change in x. Visually, what are we doing? We're looking at this little triangle right here. The side of this triangle right here is delta y. That side is delta x necessarily, right? This is c plus a delta x. So this distance is delta x, okay? When c plus delta x is evaluated into f, we get a change in y. The y value changes because we've changed the x value. Divide those two things, you get the slope of that secant line that goes through it. Here's that formula written up nicely for you. Let's try an example. Let's find the slope of a secant line through the point 1, 1, where delta x equals 1, and we're on the curve y equals x squared. Okay, so what line are we looking at the slope of? Here is the point 1, 1, right there. So there's 1. If delta x equals 1, then the other x value that I'm interested in is going to be 1 plus 1. So the second, I need a different color. Second x value. We're going to do 1 because it's the x value in the given point. And we're going to add that to 1 because it's delta x. Right? So we end up here. Okay, so our c is 1. Delta x equals 1. So c plus delta x is obviously 2. Right? The second y value, no, we're just going to follow the formula. Okay, delta x is 1. All right, so f of c in this case is f of 1. So evaluating y equals x squared, where x equals 1. Okay, that's 1. F of c plus delta x is, well, we said c plus delta x is equal to 2. So this is f of 2, which is 2 squared. So that's 4. And then, of course, our delta x equals 1. That was given, and now we have the 3 things that we need in order to find the slope. So f of c plus delta x is 4. F of c is 1. Delta x is 1. So your slope is 3. Is that right? If I actually draw that line, does it have a slope of 3? Let's look at it. I drop that line down and bring this line over. The way I've scaled this here, that distance is 3, and that distance is 1. So it works out. What about area? I mentioned we're going to eventually be interested in the area underneath a sine curve, right? This takes a little bit more doing to picture. But the general strategy is we're going to take slices, something like this. Now, if I could find the area of each slice, I could add those up, and that would total up to the area of the thing that I want. But, the problem is we've still got these curvy things on top. So what I want to do is I want to break this problem down into areas of rectangles, like this. All right, so I'm missing some area out of there. See, this pink stuff is the area that is not going to be accounted for with this strategy, which is a bummer. For now, this is an estimate. How do we do that? Well, we look at area equals width times height for a rectangle, right? Let me pick, let's say, this particular rectangle here. If this is C and this is C plus delta x, then the width is equal to delta x. What about the height? Look at where the height ends up. It's right here. The height is going to be whatever the y value is right there. And the way I've drawn this, that height is f of c. So the height is f of c. So the area of one rectangle is delta x times f of c. That gives me just that area specifically. Well, we're going to need to repeat this many, many times. We're going to need to repeat this 11 times, however many rectangles you might have under that curve. 11, by the way, is a fun way of saying a really big number. 11 could be equal to over 9,000 or 526 million, something like that. Arbitrary, really big number, 11. Okay, but that's just one rectangle. We need to do that for like delta x times f of c1 plus a delta x times f of c2, so we're going to have all different x values where we're going to do that. Add those all up, and we get those areas of the individuals. How do we deal with that little bit that's left over? The answer to that question is we use a limit. I don't want to say excess because it's not extra. I'll say unaccounted for. Okay, and the idea of a limit here is this gets more and more accurate the more rectangles you draw. So to draw more rectangles, you make delta x smaller, right? And so that leaves behind less of that pink stuff. And this happens in Unit 4. Similarly, we could ask questions like, how does a limit help the tangent line problem? Well, we had some kind of curve with an x value c, hits that y value c. Let me draw this a little bit differently. I'm trying to think of how I want this curve to look to best show what I'm trying to show. Yeah, I think that'll do it. If I make delta x kind of big over here, then the slope of that secant line isn't really doing a good job approximating the slope of that tangent line. But if I move it closer, if I make delta x smaller to put me here instead, it's going to get closer and closer. So when delta x gets smaller, the slope of the secant line gets closer to the slope of the tangent line. And there we have it. That's our introduction to calculus. Now you know a little bit about what calculus is and where it's trying to go, so that as we study limits in the next couple sections, you'll have an idea of what we're trying to do. Have a wonderful day.